Welcome back to Fun Facts Online. Today we are doing a deep dive into the engine room of the future. We are going to look at the periodic table, not as a chart on a chemistry classroom wall, but as a map of geopolitical power, economic viability, and environmental destiny. For decades, the so-called Green Revolution has been held hostage by a very specific, very expensive corner of that map. We are talking about the bottom right of the transition metals block. You know the names: platinum, palladium, rhodium, iridium. These are the noble metals. They're named for their resistance to corrosion and oxidation, essentially their refusal to interact with the chaotic world around them. But in the modern world, they are defined by something else: scarcity. These metals are the gatekeepers of modern catalysis. If you want to split water into hydrogen to create clean fuel, you have to pay the toll to iridium. If you want to scrub toxins from a car exhaust, you pay the toll to palladium. And if you want to turn carbon dioxide, the most abundant waste product of human civilization, back into fuel, you have traditionally paid the toll to ruthenium. But a quiet revolution is dismantling this aristocracy. It is a shift from the noble to the necessary, from the rare to the robust. And at the center of this shift is element 25, manganese. Manganese is the worker bee of the periodic table. It is the third most abundant transition metal in the Earth's crust, trailing only iron and titanium. It is dug out of the ground in Australia, South Africa, Gabon, and Brazil by the millions of tons, primarily to harden steel. It is cheap. We are talking about a metal trading at roughly $1.30 per kilogram. Compare that to iridium, which trades at a staggering $150,000 per kilogram. For a century, chemists dismissed manganese as too base, too reactive, and too prone to oxidation to serve as a delicate catalyst for fine chemical transformations. But that view has now been shattered. A breakthrough collaboration between researchers at Yale University and the University of Missouri has unlocked what they call the Manganese Cycle. This is a catalytic process that converts atmospheric carbon dioxide into formate, a liquid fuel and hydrogen carrier, with an efficiency that rivals and even surpasses the best precious metal catalysts. This is not merely a chemical curiosity, it is the blueprint for a new energy architecture. We are moving toward a formate economy, where renewable energy from wind and solar is stored not in heavy lithium-ion batteries or high-pressure hydrogen tanks, but in the stable liquid bonds of formate. In this episode, we are going to explore the deep science, the engineering challenges, and the economic seismic shift of the manganese cycle. We will journey from the molecular orbital interactions of a hemolabile pincer ligand to the macroeconomics of global mining, dissecting how a common metal might just save a warming planet. To understand why this breakthrough is significant, you first have to appreciate the difficulty of the reaction itself. Carbon dioxide is a thermodynamic sink. It is the ash of combustion. It is a molecule so stable that it typically takes massive amounts of energy to break it apart or force it to react. Turning CO2 back into a fuel is like trying to unburn a match. The target product here is formate, or its protonated form, formic acid. Think of this as the simplest liquid fuel. It is effectively liquid hydrogen. While hydrogen gas is notoriously difficult to store, requiring 700 bar pressure tanks or cryogenic temperatures of -253 degrees Celsius, formic acid is a liquid at room temperature. It contains 53 grams of hydrogen per liter. That is a density comparable to compressed hydrogen gas, but without the explosion risk or the energy-intensive compression infrastructure. For years, the gold standard for hydrogenating CO2 to formate was ruthenium. Ruthenium pincer complexes, molecules where a central metal is held in a vice-like grip by a tridentate ligand, could churn out formate with high turnover numbers. The turnover number is just a measure of how many times a single catalyst molecule can perform the reaction before dying. But ruthenium suffers from the precious metal paradox. The better the technology gets, the more expensive it becomes to scale, because the demand for the rare metal spikes. To make CO2 hydrogenation a global solution for climate change, we need to process gigatons of carbon. There is simply not enough ruthenium in the Earth's crust to build the millions of reactors required. Manganese was the obvious alternative, but it had a fatal flaw: stability. Precious metals are soft and hold on to ligands, the organic scaffolding surrounding the metal, very tightly. Manganese is hard and electropositive. Under the harsh conditions of a reactor, high pressure and high temperature, manganese catalysts tend to fall apart. The metal center gets exposed, reacts with oxygen or water, forms manganese oxide, which is essentially rust, and precipitates out of the solution. The catalyst dies. This is where the breakthrough from the labs of Nilay Hazari at Yale and Wesley Bernskoder at Missouri changed the game. The team didn't just swap metals. They redesigned the environment in which the metal lives. They utilized a class of ligands known as pincer ligands, specifically a variation of the phosphorus-nitrogen-phosphorus structure. I want you to imagine the catalyst as a crab. The manganese atom is the body. The ligand provides two claws, the phosphorus atoms that grip the manganese tightly, and a mouth, the nitrogen atom that anchors the center. This tridentate grip forces the manganese into a specific geometry that is perfect for grabbing CO2 molecules. But the innovation was the introduction of a concept called hemolability. In a standard catalyst, the claws are locked shut. However, the Yale and Missouri team added an extra donor atom, a molecular safety valve, to the ligand structure. This extra arm is hemolabile, meaning it can bond and unbond to the manganese center as needed. Here is the genius of the mechanism. First, you have the resting state. When the catalyst is idle, the hemolabile arm wraps around the manganese, protecting it from reacting with contaminants or falling apart. It effectively puts a shield up. Then comes the active state. When the reactants, the CO2 and hydrogen, approach, the hemolabile arm pops open, creating a vacant site, essentially an open parking spot on the metal where the reaction can take place. The CO2 inserts itself, hydrogen is transferred, and formate is ejected. Finally, the recovery. Once the product leaves, if there is no immediate new reactant, the hemolabile arm snaps back into place, reshielding the metal. This breathing mechanism solved the stability crisis. For those of you chemically inclined, the cycle proceeds through a fascinating metal-ligand cooperation pathway. It begins with the manganese pincer complex. Molecular hydrogen approaches. The arm of the ligand assists in splitting the H2 molecule. One proton attaches to the nitrogen of the ligand, and the hydride attaches to the manganese metal. This creates a charged, energy-rich species called a manganese hydride. A molecule of CO2 drifts nearby. The manganese hydride is nucleophilic, meaning electron-rich. It attacks the carbon atom of the CO2. The CO2 gets inserted into the bond. The hydride jumps from the metal to the carbon, turning CO2 into a formate group bound to the metal. The formate molecule must then detach so the cycle can restart. In previous manganese catalysts, the formate stuck too tightly, poisoning the catalyst. The new ligand design, however, facilitates a rapid release, possibly aided by the hemolabile arm physically pushing the product out. The researchers achieved turnover numbers in the tens of thousands, proving that earth-abundant metals, when dressed in the right organic clothing, can perform noble work. But a catalyst is useless without a system. The manganese cycle allows us to make formate efficiently, but what do we do with it? This brings us to the consumption side of the cycle, and the direct formic acid fuel cell. The world is trying to move to hydrogen, but hydrogen is a logistical nightmare. To ship hydrogen, you must liquefy it or compress it. This consumes 30% of the energy content of the hydrogen just to store it. Hydrogen leaks are invisible, odorless, and explosive. And we have millions of miles of pipelines and tankers designed for liquids like oil and gasoline, not high-pressure gases. Formic acid is the Goldilocks solution. It is a liquid at ambient conditions. It can be pumped into existing tanks. It can be shipped in standard chemical tankers. And most importantly, it carries hydrogen in a safe, chemically bound state. There are two ways to get energy out of formate. Method A is the reformer. You can run the manganese cycle in reverse. Using a similar catalyst, you can strip the hydrogen back off the formate. You get a stream of pure hydrogen gas and CO2. The hydrogen goes into a standard fuel cell to make electricity. The CO2 is captured and sent back to the start of the cycle. The advantage is that it uses existing high-efficiency hydrogen fuel cells. The disadvantage is that it requires a reformer unit, adding weight and complexity. Method B is the direct formic acid fuel cell, or DFAFC. This is the holy grail. In a DFAFC, you don't strip the hydrogen out first. You feed the liquid formic acid directly into the fuel cell anode. DFAFCs are inherently safer and simpler than hydrogen fuel cells. They operate at low temperatures, from room temp to 60 degrees Celsius. Recent research from 2024 to 2026 has made massive strides here. While we use manganese to make the fuel, we often use palladium to burn it. New alloying techniques with iridium have created anode catalysts that resist carbon monoxide poisoning and boost power density. Furthermore, new membrane technologies using graphene oxide have drastically reduced crossover, allowing for higher concentrations of formic acid fuel to be used, which boosts the energy density of the system to rival lithium-ion batteries. Now, let's talk about the economics of abundance. The scientific elegance of the manganese cycle is matched only by its economic brutality. It is a story of raw cost. Let's look at the numbers for the metal precursors used in these catalysts, based on recent market prices. Iridium is around $155,000 per kilogram. Rhodium is $140,000. Ruthenium is $15,000. Manganese is $1.30. The difference is not a percentage. It is orders of magnitude. A manganese catalyst is effectively free compared to its ligand synthesis cost. For a global energy system, this scaling factor is non-negotiable. If we were to replace 10% of global fossil fuel usage with a formate cycle using iridium catalysts, we would need more iridium than exists in the entire crust of the Earth. With manganese, we would barely make a dent in global annual mining output. Then there is the geopolitical security. The green energy transition carries a risk of replacing dependence on petrostates, like Saudi Arabia and Russia, with dependence on electrostates. 70% of cobalt comes from the DRC, 80% of rare earths are processed in China. 90% of platinum group metals come from South Africa and Russia. Manganese, however, is geographically diverse. While South Africa is a major producer, significant deposits exist in Australia, Gabon, Brazil, India, and Ukraine. Deep-sea nodules in the Pacific are also rich in manganese. It is a strategic metal, yes, but it is not a monopoly metal. A manganese-based energy cycle is inherently more democratic and resilient to geopolitical shocks. Because manganese is so cheap, it also changes the engineering philosophy. With ruthenium, you must recover 99.999% of your catalyst after the reaction, because losing it bankrupts the process. This requires expensive filtration and recycling steps. With manganese, while you want to recycle to be green, the economic penalty for catalyst loss is negligible. This allows for simpler reactor designs. You could potentially run flow reactors where the catalyst is immobilized on a cheap support and replaced every few months like a simple water filter, rather than the complex recovery loops required for liquid noble metal catalysts. So how does this look in the real world? Imagine a wind farm off the coast of the North Sea, or a solar array in the Arizona desert. The renewable source generates electricity. This electricity drives a water electrolyzer, producing hydrogen. Next door, a direct air capture plant or a cement factory flue stack captures CO2. The hydrogen and CO2 are piped into a high-pressure reactor containing the manganese pincer catalyst. The gas mixture bubbles through a solvent containing the catalyst. The hemilabile arms of the ligands open and close billions of times a second, knitting hydrogen and carbon dioxide together. The output is pure formic acid. This liquid formate is pumped into standard storage tanks. It is non-flammable at room temperature. It can be stored for years without degrading, unlike batteries which lose charge. It can be loaded onto trains, trucks, or ships. At night, when the solar panels turn off, the formate is fed into a large-scale fuel cell facility to push electricity back into the grid. Or, a heavy-duty truck pulls up. Instead of diesel, it fills up with formic acid. Its onboard fuel cell converts the liquid to electricity to drive the motors. The only exhaust is CO2, which was captured from the air originally, and water. While the Yale and Missouri breakthrough is academic, the commercial ecosystem is revving up. Startups are exploring the commercialization of CO2 to methanol and CO2 to formate pathways. The manganese moment is attracting venture capital because it solves the capex problem. Building a plant that requires $100 million in iridium inventory is hard to finance. Building one that requires $50,000 in manganese inventory is a much easier sell. Despite the optimism, the manganese cycle is not a done deal. Engineering hurdles remain. Most manganese catalyzed hydrogenations currently require a base, like an amine, to help pull the proton off the H2 molecule. This means you don't produce pure formic acid, you produce a formate salt. To get the fuel out of the salt, you need to acidify it and separate it, which creates waste. The next generation of catalysts is targeting base-free hydrogenation. We also have to consider solvent effects. The catalyst works best in specific organic solvents. For a truly green process, we want it to work in water. Designing hydrophobic pockets around the manganese center is the next frontier. And finally, energy efficiency. Every step incurs a loss. The round-trip efficiency of a formate cycle is currently lower than a lithium-ion battery, but batteries are great for hours of storage. Formate is for seasons of storage. You cannot build a battery big enough to store summer sunshine for winter heating. You can fill a tank with formate. In conclusion, the definition of a fuel is changing. For a century, fuel was something we found: coal seams, oil reservoirs, gas pockets. In the 21st century, fuel is something we make. The transition to synthetic fuels has been stalled by the cost of the machinery, the catalysts required to knit molecules together. We have been trying to build a global renewable infrastructure using the jewelry of the periodic table. It was never going to scale. The manganese cycle represents the democratization of this technology. By teaching a common, abundant metal to perform the complex dance of hydrogenation, scientists have removed the scarcity constraint from the equation. The Yale and Missouri breakthrough is more than just a clever ligand design. It is a permission slip for the developing world to participate in the hydrogen economy without being beholden to rare metal monopolies. As we look toward 2030 and 2050, the steel towers of wind turbines may well be supported by the same metal that facilitates the energy flowing through them. Manganese, the element that hardened the Industrial Revolution, is now poised to catalyze the Green Revolution. The cycle is closed. The toll booth is open. The era of formate fuel has begun.